Hello, ladies and gentlemen. My name is Vasiliki Lazari, and it's a great pleasure for me to present at the Construction in the 21st Century 12th International Conference the paper Electric Vehicle Charging Stations Deployment Optimization Using Genetic Algorithms. The EV charging stations placement problem is one of the most challenging optimization problems in the transportation sector and in the field of infrastructure management. It's a combinatorial optimization problem based on the facility location optimization problem with multiple and competing objectives and constraints whose complexity grows with the problem size. Existing studies generally attempt to solve this problem by creating models which use a predefined list of candidate locations for charging stations to be deployed, as well as a predefined number of stations to allocate. The objective of the study is to develop an optimization model that determines freely the optimal locations to place the charging stations within an area of interest and the number of stations that should be allocated, with the goal to maximize the electric vehicle user satisfaction, meaning to minimize the travel distance, and minimize the construction, operational, and maintenance costs for the charging stations deployment, while considering EV fleet assignment as a second level of the problem. The analysis aims to search for the most efficient locations for positioning the charging stations within the area of interest and provide suggestions on the number of EVs that can make use of the charging station daily so as to ensure that the solution meets the charging demand per day. The methodology proposed to achieve this goal consists of 7 main steps. The first step is to formulate the cost objective function as the cost summation of all optimization sub-objectives. In this work, 2 objective goals have been proposed and evaluated for their efficiency in approaching the global optimum and in minimizing computational time, which incorporate A, the cost for deploying a network of charging stations, representing the sum of costs for land acquisition, construction, operation, and maintenance, and B, the cost of traveling distance, representing the sum of units traveled by the users from the charging demand point to the nearest charging station. The second step is to set priorities for the station's deployment by parameterizing unit cost values for every sub-objective. Then, after considering any constraints needed to be included in the analysis, the optimization model is implemented in an Excel spreadsheet. The next steps are to choose the optimization method and algorithms to solve the problem, which in this case are the genetic algorithms, and afterwards parameterize algorithm characteristics such as the mutation and crossover rates. The following step is to perform the optimization by the commercial optimization software Palisade Evolver 8.1, and lastly test different case studies and compare the produced results. In this analysis, 3 main case studies with a project consisting of a 200 EV fleet are considered in order to illustrate the algorithm application. All case studies use the same unit values for parameters W1 and W2 and the same cost per station. Case study 1 searches for the optimal station allocation by examining 25 different scenarios where the charging station network is composed of 1 to 25 stations respectively, which all of them are initially placed at coordinates 0.0. Case study 2 also tries to find the optimal station allocation. However, it focuses on a network of 12 charging points with an initial allocation setting in the form of X, in order to examine whether a different initial setting could be a parameter that affects the model efficiency. In case study 3, the number of charging stations is considered as a decision parameter in addition to the optimal station placement. More particularly, the algorithm was redeveloped to identify both the number and the location of the charging stations. Looking into the produced results derived from case study 1, it appears that the travel distance decreases with the increase in the number of charging stations being deployed. However, the number of charging stations should be determined and kept under certain limitations based on the charging demand, the size of the area of interest, as well as the restriction in budget availability. The classical trade-off diagram between the charging station number and the traveling distance shows the impact of a change in each attribute to the other attribute and how this may affect the decision-making, minding the special characteristics and constraints of the problem. For example, if the main goal is to keep the traveling distance for the drivers under 2,000 units, the optimal number of charging stations is 10, providing that the available budget is over 10,000 units. In case that the budget is limited to 8,000, then 8 charging stations may be constructed in order to approximate the initial goal of the traveling distance. Based on the objective function cost diagram, it can be seen that the minimum value is 28,341 units, which corresponds to scenario 12. This means that the scenario 12 leads to the overall best solution among all scenarios for the existing demand size and origin. The charging station allocation of the best solution is depicted in Figure 4. Figure 5 portrays the relative convergence function rate for 4 indicative scenarios. As expected, the rate of convergence decreases with the number of charging stations. Among the presented results, scenario 10 presents the fastest rate of convergence as it's reaching its optimal solution after approximately 110 seconds of runtime, while scenarios 15, 20, and 25 are developing the optimal solutions after 250, 500, and 650 seconds, respectively. The optimization results of case study 2, which is built upon scenario 12 representing case study 1 best solution, indicate that the algorithm converges to the same solution of scenario 12 regardless of the initial station placement. Regarding case study 3, several tests were performed considering an initial number of stations ranging from 15 to 25 and being initially placed at coordinates 0.0. In general, the model presented a convergence to a solution consisting of 12 stations with a minimum value solution that coincides with those of scenarios 12 and next from case studies 1 and 2 respectively. To sum up, this study proposes a model which utilizes genetic algorithms to formulate a flexible tool for planning the location of charging stations infrastructure. Multi-criteria analysis was performed to account for user traveling distance and charging station development cost. The model can provide the optimal number and locations of charging stations in an area with scattered demand for EV charging. Several test cases and scenarios were developed and evaluated for a rigorous assessment of the optimization model performance. For instance, additional tests were made in which the demand was considered as concentrated in specific points randomly placed within the study area, for which the algorithm succeeded to place the stations exactly upon the points of the demand existence to fully eliminate the transportation cost. In regards to the selected algorithm, it should be highlighted that due to algorithm's special characteristics, the obtained solution may not necessarily be the optimal one in every single run, and especially as the problem grows up in size. To improve the success rate, the algorithm was run repetitively so that, considering the stochastic nature of it, to obtain more viable solutions. Based on all the aforementioned results of the analysis, genetic algorithms appears to be an appropriate method to attain the reasonable planning for the EV charging stations, considering the priorities and objectives in every test scenario. Thank you very much for your interest and attention.